After DPCM, we are going to discuss delta modulation. Delta modulation is just like DPCM, but it is 1-bit DPCM. That means it is a DPCM that uses only two levels. That means L equal to 2 for quantization of the difference signal D, which is equal to the message minus the expectation or estimated value of the message and its quantized version. So in comparison to PCM, it is a very simple and inexpensive method of analog to digital conversion. Now in delta modulation, we use a first order predictor, and a first order predictor is nothing but a delay. So the circuit that we have already discussed in connection with DPCM will be almost identical for delta modulation, and the only difference is the predictor circuit. So let us redraw it. This is message, this is the difference, this difference is nothing but the estimated value is nothing but the previous signal. Here we have the delay. Instead of predictor, we have simple delay. Here we have dqk that will be transmitted in the feedback path, just like previous one. So this will be the circuit for the delta modulation, and just like DPCM, this section this portion will be the receiver portion. So receiver portion, if we draw it in a separate way, this is the demodulator part. Now we have already analyzed the DPCM, and from that analysis, instead of going to the details of that, here in this portion MQK is nothing but the addition of MQK minus 1 and DQK, right? So we can write MQK minus 1 equal to, it is a recurrence relation, so MQ K minus 2 plus DQ K minus 1. If we put K equal to K minus 1, then we can write this. Now putting the value of mqk minus 1 here, we can write mqk equal to, replacing this value, mq k minus 2 plus dqk plus dq k minus 1. Now if we proceed further, putting k equal to k minus 2, k equal to k minus 3 and so on, ultimately we will get mk minus k, that means m0. Now just assuming the initial condition, that mq0 equal to 0, we can write from this equation, proceeding in the similar fashion, mqk is equal to summation of and this is very interesting because at the right hand side, as you can see, that there is no term associated with m. That means we are not transmitting the actual message at all. We are all the time transmitting the difference between the previous signal and the current sample. So receiver of this one is nothing but an adder or accumulator. Now if the output dqk is represented by impulses, then the accumulator may be realized by an integrator, because its output is the sum of the strength of the input impulses. So we may also replace the feedback portion of the modulator by an integrator. The demodulator output will be mqk, which when passed through the low pass filter is the desired signal constructed from the quantized sample. So if we use this logic, we can modify these two circuits in this way. This is the switch, S is the switch, and the switch is closing at a rate of Fs. Fs is the sampling frequency. So here we have dqk, and the nature of this dqk is like this, something like this. Now in the feedback path, we have an integrator. So this is the modulator circuit, this one is the comparator, and this one is the integrator. Similarly, we can draw corresponding receiver. Receiver is very simple, integrator along with low pass filter. We should get back the replica of the original message. So this is the demodulator, this one is the modulator for the delta modulation. It's a practical circuit. So here the first order predictor, rather this delay is actually replaced by a low cost integrated circuit, and the modulator consists of a comparator and a sampler in direct path and an integrated amplifier in the feedback path. Now let us see how it works, and for that we assume a signal. Say this is our signal, any arbitrary signal, something like this, and here we will plot is D. So this one is M. So what happens? When it is switched on, this M is at this position, and the integrator output MQ cap, it is the integrator output, and at first it must be 0. So integrator output is here. Now what the comparator will compare? Comparator will compare this D, but this D is nothing but MT minus MQ cap T. It means that if D is greater than 0, it will produce plus E. If it is less than 0, then it will produce minus E. This is the job of this comparator. So M is here, integrator output MQ cap is here, so D is positive, so it will produce a positive E volt. That means DQT will be a positive voltage, right? Now this switch will momentarily closed, and once it is closed we will get DQK. So what should be the value of this DQK? It will be a positive impulse, positive volt of plus E. So it will be a positive volt plus E at this particular point, then it will be switched off again. But that DQK, that means this impulse will fed back through this integrator. So what the integrator will do, once it receives this one, it will increase its value by certain amount and it will continue, because it is integrator. So again it will compare this D. So at this point here, this is M, this is MQ cap. Again M is higher, so D will be positive, so DQT will be plus E volt, and we will get another positive spike right here. So at this position we will get another positive spike, and it will be like this. So in this way we will get positive spikes, and the integrator output will follow or try to follow the input signal in a staircase fashion. Now consider this situation. Here the situation is just reversed. In this case MQ cap T is higher than MT, so D will be negative. Once D is negative, it will produce a minus E. That means here we will get a negative spike. Negative spike. So once we get this negative spike, that will be fed back. So integrator output will move in a downward direction by same amount, and it will continue. So in this way, here actually this one will be a positive voltage, 1 2 3 4, this one will be positive, and here we have the negative. At this point we have the negative voltage. Again at this point, MQ cap T is lower compared to M, so D will be positive. So again here this dqk will be a positive spike. So at this point it will be a positive spike and it will move in upward direction. So in this way, in a staircase fashion, the integrator output will try to follow the input signal, and we are actually sending this information, this D. At the receiver side, so this one is dqk actually. We are actually getting dqk. So we are actually getting these things. So that is given to the integrator. So integrator will produce this type of a staircase waveform, and the low pass filter will eliminate the high frequency component from this staircase, and the original message or replica of the message will be recovered. This is how the this demodulator works. One thing you must note that each sample at each point, these are the sample values, and these samples may be transmitted with the help of just 2 bits, one for positive impulse, another for the negative impulse. So this is why it is, that is why it is a single bit DPCM. Now for proper operation, this Fs must be much higher compared to the Nyquist rate. So this is the condition that we have to maintain. Now this delta modulation, there are two major sources of error. One is the slope overload distortion, and another is the granular noise. So let us see what is the meaning of slope overload distortion and granular noise. Generally, this, if you call this as step size sigma, then the sigma is constant for a particular circuit. The sigma is constant, the step is constant. Now if we have a signal that varies at very fast rate like this, this is M. So what happens? The integrator output will try to follow this signal in a staircase fashion like this, because integrator cannot move. This one is sampling time, and this one is sigma. So integrator has a maximum slope, and if that slope is different from that of M, the message signal slope, then the integrator will not be able to follow the original message signal. So here we have the error, and this is called the slope overload distortion. So slope overload distortion occurs when the slope of the message signal is very high compared to the slope of the integrator. Now to understand this granular noise, let us extend this with a very small change in the signal. So what happens within this region, the integrator output will be like this. It will move up or down in this way. That means the signal is stable almost, but the output is moving continuously. It is just like quantization noise in PCM system. This is what we call, that will produce some noise, and this change in signal that is producing some noise is called the granular noise for delta modulation. So these are the two drawbacks of this delta modulation. Now if we try to recover from any one of the problems, say we want to reduce this slope overload distortion, so what we have to do, we have to increase this sigma. That means at one step it will move at higher value, but in that case the granular noise will be higher. In other words, if we want to reduce this granular noise, the step size must be smaller. The step size must be smaller. But once the step size is smaller, then the slope overload distortion will be higher. So that is a conflicting situation. If we want to reduce this slope overload distortion, granular noise increase, and vice versa. So what we can do, we can use another technique called the adaptive delta modulation, ADM, where the step size is controlled automatically. When the slope is higher, the step size increases, and when the slope is low, that means the signal is flat, the step size will be reduced. This is what is done in adaptive delta modulation. We will discuss later on. Now we will try to find out no slope overload condition. No slope overload condition. That means we have to determine some condition where the slope overload distortion will not occur. As we have said already, that sigma is the step size and Ts is the sampling time interval. So MQ cap T, that is the integrator output, is capable of changing by amount of sigma. So the maximum slope that MQ cap, the integrator output, can follow is sigma by Ts, or that is equal to sigma into Fs. Fs is the sampling frequency. So no slope overload distortion occurs if the slope of the message signal m dot t, its magnitude, is less than Fs. This is the condition for getting no slope overload distortion. That means the slope of the message signal must be less than that of the slope of the integrator. Let us take just one example. Say MT is some sinusoidal variation. In that case, m dot t, its magnitude, is equal to omega into A. And according to this relation, this omega into A must be less than sigma into Fs. So maximum amplitude we call it as a Amax of this signal that can be tolerated without overload distortion can be written as sigma Fs by omega. So for a system we can get no slope overload condition when MT is a sinusoidal variation. Maximum amplitude of the signal may be determined from this relation. Application of delta modulation, it may be suitable for low bit rate voice communication. Other applications may be there, but this is one of the major applications.